Okay, next topic. We want to improve our approximations, and we also want to say, we know that as n gets bigger, right? If we just jam more rectangles in there, if n gets bigger or the width of every rectangle gets skinnier and skinnier and skinnier, we know then that our approximations have to improve. No matter what rule we're using, that's the case. Just make n bigger and you're going to get a better approximation. But the question we might want to know is, well, if n was 100, how good is it? Like, can we get a bound on this error, these little black shaded regions? Can we bound that and say, well, if I want, for a particular application, I need this to be within 10 to the minus 6 or 0.00001. Like, I need that level of precision in my approximation of the error. Can we do that? And there is a really nice way to do this. This is towards the end of chapter 1 of book 1.5. We're going to talk about error analysis. And so first thing I want to do is just go back to the tech tool. And we were looking at, I think we were with Wolfram, right? Yeah, we've gone to Wolfram Alpha, and you can enter things like write endpoint rule for y equals our same function x cubed minus x plus 1 on the interval from -1 to 3. Those are x values with n equals 20 interval. So you can kind of type it as you would in, this is a natural language processing tool. So you try to get as close to English, and then just make sure that it's interpreted what you've typed in correctly and you've typed it incorrectly. We have the function y equals x cubed minus x plus 1. There is our plot from -1 to 3. Oh wait, I must have something slightly off in how I've entered this. So I'm going to check the tech tool page in chapter 1 just to make sure I got the vocabulary right. Okay, so I've entered now. I just want to show you another way to get to the Riemann tool. I just went to Wolfram Alpha and I entered Riemann sum and went to the computation part. So maybe a better way of showing this. Let's see what happens when I get the first time. Riemann sum, and then it's showing you like pictures and a definition, and assuming that you're asking for a definition, but if you want to do it as a computation. And then it shows you that you can change your function. So we want x cubed minus x plus 1. But we also want to include the range. We want to go from, x goes from -1 to 3. But we also want to get the width of the interval. So the interval size, they're saying 0.5. We originally started with intervals of size 1. And so then it's showing that, again, we'll get to this word integrate in chapter 2, the left rule from -1 to 3. Here's what the left gives of 10, the right was 34. And yes, we did those last video. And you can watch what happens as you shrink the width, which is the same thing as increasing the n. So let's say we make those 1/10 smaller. So really we're then doing a total of 40. So 4 times 10 is 40n. So we're really making 40 skinny little rectangles. Each rectangle has a width of 1/10. So skinny little thing. This one I don't think shows a picture like Desmos did, but let's see. Okay, so now we're getting better approximations with the left and the right. The exact area is actually 20. Again, they show that. We won't understand how to do that till next chapter. But you can see that the left got better, the right got better, the midpoint got really darn close. Let's maybe shrink that again by a factor of 10. So really we're doing each one is 0.01, 1/100th of a width, so slivers. And we're slamming 400 of them then. N has the width of x is 4, and then we're putting 100 of those in each interval. So we're going to get 400 as our n. Another way of thinking about it, or just shrinking the width. Same exact value of 20, and when n was 400 then, and the width is just 1/100th, we're getting the left endpoint is 19.88. So with a really big n, we're still not even, have any decimal places of accuracy. Same thing for the right. I mean, we're still not there on our exact value. If you need precision, we're talking about like building airplanes or something, that's not going to do, right? So we can just keep shrinking this and just see how close we can get. This is now doing like n is 4,000 in this case. It takes a little longer for it to compute. Okay, 9.98 with the left. Now the midpoint's pretty close. It's saying it's within 10 to the -6. We'll talk about that error. That's actually the point of this lesson. But the first thing I just wanted to show you with a tech tool that loves to crank away, that we're still just getting, we're still not that precise even when n is really big. So you'd have to do, even n equal 1,000,000 sometimes will only give you, say, 4 or 5 decimal places of accuracy. If you're an application that needs more than that, then you're going to have to figure out how to at least bound that error, or move on to chapter 2. And so we're going to get to that soon too. Okay, so again, first moral is that increasing n improves your approximation, but it doesn't mean it gets the level of precision that you need for a particular application. And so how can we decide what is the appropriate level of precision that we need? So we're now at the end of chapter 1 of journal 1.5. We're going to talk about error analysis. So there's a couple pages at the end that talk about error. And we're going to look at what's in the box here. And we're going to apply that to our particular problem here. So we have the same function, same region. And I'm not going to draw pictures with like 400 rectangles. That would be crazy. But we are going to see if we can bound the error. And so there's this formula that you're going to need to use. That applies to the midpoint rule. So this EM, the M stands for the midpoint rule. So had you applied the midpoint rule, this is going to give a bound on your error. It's going to say your error is about this big if you used a certain n. So let's say, for example, that we wanted to wonder how big n would be if we did, so find the error, EM, associated with n equals 20 and the midpoint rule for that function over that region. So had you used 20, how good can you expect it to be? What is, are we 0.001 within that of the true value? So again, we don't know the true value, but we can bound it. This is a really neat part of mathematics. Even though we don't know, forget the fact that Wolfram told you the exact value is 20. Even though we don't know that, we'll be able to come up with a value that says your error is no more than this value. Like if it might say the error is within 0.01, so you're within 2 decimal places. It might say it's within 0.001, you're within 3 decimal places of the correct answer. So that's useful information. Okay, so let's find that for this particular problem. Well, it's really just applying the parameters of your problem to this inequality. So we can say that our error, absolute value of the error is within K. I have to tell you what that is. So we're going to come back to that. But we do know what B and A are. Those are your endpoints. We go from -1 to 3. So this will be 3 minus a -1 cubed all over 24. And then N was 20, so we square that. So we're going to take 24 times 400. So we're going to have K. Again, I'll tell you what that is in a moment. 4 cubed is 64 over 24 times 400. Now K, if you look in the box, the error rule, K is a bound on your second derivative of your function. So we got good from book 1 at taking derivatives. So let's get the first derivative for our function power rules, 3x squared minus 1. The second derivative is 6x. And now k says on the interval from -1 to 3, what's the biggest value 6x could take? Well, you could actually think about this graphically. 6x is just this line. From -1 to 3, the biggest value that would take on is right here. And that would be the point 3. 6 times 3 is 18. Another way you could just look at it right here and say, what's the biggest? When x goes from -1, I get a -6. When x goes all the way up to 3, I would get 18. So the biggest value, so that's the k. K actually becomes this 18. That comes down here and is your k. So it's the bound on the second derivative. It's the biggest, the maximum value that your second derivative would ever have on your interval from a to b. Okay, so let's go ahead and use a calculator to figure that out. I'll do this real quick. You can also just do, like Google has a calculator. If you just say equals, and then we'll put in our numerator is 18 times 64. And then our denominator, we'll divide that by 24 times 400. And that's 0.12. So when n is 20, you're within 0.12 of the true value. So we won't even get 1 decimal place of accuracy, and we saw that when we did our Wolfram Alpha and our Desmos examples. We saw that this mid rule was better than the left and right, but it still was 19.8, I think, at that point, and the true value is 20. So again, even though you don't know it, you can say you're within some region. So you're plus or minus 0.12 of the true value. And maybe that's not good enough. Again, maybe you want to say, what do I have to do? So maybe we'll put that in the picture here. Let's ask another question. Maybe we want to find how big n should be so that we get 4 decimal places of accuracy. Okay, well, we actually have the information here to answer this. If you want 4 decimal places of accuracy, that's saying you want your EM to be less than 0.0001, let's say. So you can translate that places of accuracy to some value you want to be within plus or minus 0.0001 of the true value. And so we're going to start plugging in some things here and solving for n this time. We didn't fix n, we're going to find n. See, in this one, we fixed n at 20, and we found the error. Now we're going to assume an error and find an n. And we have this inequality that's going to help us do that. So we want this to be less than 0.0001. We already found our k from before was 18. So we'll put in the particulars for our problem. B minus a cubed, that was 4, cubed is 64. And now we want to solve this inequality for n. We just want to move some stuff around and figure out what's the n that's going to make this true. So 18 times 64, let's see what that is. $11.52. So the numerator is 1152. And then let's multiply both sides by 24n squared, and so we'll get 0.0024 n squared. Divide both sides by the 0.0024. So we have n squared, and then this fraction over here, 1152 divided by 0.0024. We get a decimal. I'm sorry, we get a 480,000. And then we need to solve for n. n is stuck inside a square, you do the inverse operation, square rooting, whatever you do one side, you do the other. So we'll get n is compared to this square root of 480,000. Let's just go ahead and get that calculator help us. $692.82. N has to be bigger than that, right? So you can flip the inequality around, and that tells us n is at least bigger than that. And we don't really care about decimals, so we say n is greater than or equal to 693. If you set your n bigger than 693, you're guaranteed your error is within 0.0001 of the true value. So again, this is a nice inequality, the inequality in the box. It's a really nice inequality that'll help you with the midpoint rule. I only put midpoint in this chapter, but there's other ones that exist. Like for instance, for the trapezoid rule, you can figure out how big does n need to be to guarantee particular accuracy. Of course, if we want to be more accurate, you solve this inequality again, you'll see n has to be bigger. That all makes sense, but now you have like a precise value of the amount of work that needs to be done. Okay, I think that's the last comment. So from chapter 1, some of the main things you learned from chapter 1, how to approximate areas of unusual shapes, any shape, but for us, we always go from a function to an x-axis, from a left endpoint to a right endpoint. So this one, you have to take Calc 2 to learn how to do this one. But for now, anytime you go from a function to an x-axis, you can get that approximate area with a Riemann sum. The 3 you need to know how to do are left, right, and mid. You can use a tech tool to check your work. As n increases, you can see that you will get a better approximation. You can also, once you've drawn it, look at with the left, right, and mid, whether you have an overestimate or underestimate. Out of those 3, the mid's going to do the best for a given n. And then lastly, we were able to say, how good are we doing, in particular with the mid rule, with this inequality, error bound here. So with the mid, we could say, if n was 47, how good are we doing for the mid rule? And we'll get an error. And we had to use the second derivative to do that and bound the second derivative and applied it to this inequality. And then the other way we can do it is to say, with a desired accuracy, what's the n that achieves that desired accuracy? So chapter 1, approximate areas, we're about to move into chapter 2, which is exact area. For now, the best we can do is just make n bigger and bigger and bigger, which is making the width smaller, smaller, smaller. We're about to jump to exact areas with antiderivatives or integrals. All right, enjoy chapter 1.